Thanks, Ryan. I appreciate it. It's so good to be at Enigma and see so many old friends and new faces as well. So what I wanted to do in the next 20 minutes or so is share a story on a project that I've been involved with for a while now around end-to-end encryption. So let's dive in. Ryan sort of covered this, but just a couple quick things about me. These are the things that I've focused on. I think some of the folks may be familiar with some of the past projects listed here. Other things I've done that you may be aware of, in the US, the big mobile telecom carriers with the super cookie tracking, some of the work we did with the FCC. And then before kind of my public face in the security community, I did a fair amount of work with the Defense Department, Homeland Security, and then, I don't know, probably 10, 15 years in healthcare research, working on life-critical and safety-critical systems, which I think if you start your career working on systems that, for example, are administering drugs for the first time ever in humans, it sort of etches some instincts in that I think kind of inform you for the rest of your career. So with that, let's dive in. I wanted to start with some database myths and misconceptions, talk about models, both formal models as well as kind of mental models of trust systems. And then I think the rest of the bulk of the talk will be what I hope folks are interested in, which is the work we did on end-to-end encryption with MongoDB. Myth number one, misconception. So database encryption is a solved problem, right? We have no shortage of tools and technologies in our toolkit to do all kinds of encrypting techniques. And so you look in the cloud provider software development kits, you look in all the major relational or NoSQL databases, there exist different techniques to do encryption. So it should be a pretty solved problem, right? No, it is very much not. In fact, I would argue that one of the powerful lessons for me from this work that we've been doing for the last 2 years is that I'm not even sure we've got a shared lexicon in the technology space for what that even means to have an encrypted database. Whenever there's like one of these really high-profile kind of public breaches, and there's the conversations about that inevitably come up, if only the database were encrypted, then the attackers couldn't have done X or Y. But if you talk to somebody who works in sort of the regulatory world or the compliance world versus, I don't know, maybe system design or management, they have very different understandings of what encryption means. So clearly, TLS is one element of encryption, and it's an important one, right? What about storage encryption, right? So Security 101, sensitive information should be encrypted at rest. So full disk and whole disk encryption, this is kind of table stakes, I think, in a lot of cloud provider contexts. Many years ago, some of the biggest users of large-scale databases went to the makers of that software and said, we want to do something better, because actually at the time when database, what's called whole database or table space level encryption was developed, full disk encryption wasn't common at all. And so in a sense, it's sort of a stopgap measure. The idea is that the physical data store files that make up a database, why don't we encrypt those with some kind of scheme, and so provide some level of access separation or higher granularity of controls. And so that is important, and it does address certain threats, but it probably doesn't address a lot of threats that we may sort of kind of implicitly understand. So in the context of central models for databases, I'd argue we've done a pretty good job addressing, again, encryption at rest, in transit, sorry. So with modern TLS, we've learned quite a bit in the last 10 years or so with forward secrecy, with better, abuse resistance techniques, and we've discovered that the tiniest biases, the tiniest errors, the tiniest differences in timing can sometimes undermine the entire confidentiality of a payload. So I think we've gotten, between TLS itself and HTTPS, I think we've sort of developed more sophisticated understanding and some better measures. So I think in general we're doing a pretty good job there. I think encryption at rest too is not bad, right? I mean, on most modern operating systems, when you install a system, one of the first questions very early in the flow is, should this root volume be encrypted? and then it's done. It's fair to argue many people aren't super thrilled with some of the trade-offs that have to happen, but the point is that it's available, it's accessible, and it's widely used among developers and in the systems world. But the model where the database is doing encryption on records itself, that table space in the relational world, collection level or whole database, sometimes in the NoSQL world, the notion is we've got some sensitive records, we're going to encrypt them, but when the database starts up, it's going to retrieve keys somewhere, somehow, and then the system, and therefore the people who run that system, depending on their privileged access, can see the information. But who can see that plain text, right? Is it the DBA themselves? Is it the sysadmin? Usually yes, right? The database server, if you're talking from an infrastructure perspective, yep. If you've got root or ring -1, in general, there are some exceptions, but in terms of what's actually implemented in the field, in the wild, generally speaking, you've got visibility into memory, you've got visibility into mounted volumes, you've got visibility into process, which is a real issue with cloud providers, right? I would argue this is the model for most central databases, which is we're going to do all these complicated techniques, but by the way, the first thing I'm going to do is delegate my keys back to the very thing that I'm not sure I want to trust to get it to mount. So what is the source of trust, right? In these server-side encryption models, a leak or breach is catastrophic, and I don't just mean the kind of things that we see quite a bit in terms of like a cloud bucket or like a volume snapshot or an entire image that's leaked somehow. I mean the entire sort of breadcrumb, the entire digital ecosystem around a running system, right? So logs, backup files, temporary files, and crucially process memory. The assumption in most central models of encrypted databases is if you've got privileged access, either the human user or the process can see everything. It's pinky promise as a service, right? That's the trust model. I'm going to give you all my sensitive information, but they're encrypted, and the first thing I do when the database starts is I'm going to hand you my keys to then do these things that a database needs to do to operate on these values. So the main thesis of the talk is there are far fewer options available for developers to protect data in use, data that's actually being used, than you might think. And a small 6-year-old GitHub maintained by Denver Coder 9 doesn't count. And small plugins and things like this, if they're not easy to use, if they're not consumable, if they don't scale, if they don't work in different languages, then that's not really practical. It's theoretical. We've got some of these techniques and tools. A lot of cryptographers, a lot of academic cryptographers, a lot of sort of proofs of concept code, but I'm talking in widespread use in commercial and open source systems. In theory, we should be able to do a good job with this, but in practice, well, it's a big chasm between what we might be able to do theoretically and what we actually have to do if I'm a mid-level Java developer at a bank, or I'm trying to do, maintain insurance records, or I'm trying to maintain a cryptocurrency exchange, or a gaming platform, or any other kinds of sensitive records or information. As the developer, as a frontline person, those options are vanishingly few. And it comes down to this. Encryption at rest is only helpful if, in fact, we're resting, right? That vault is very powerful for the bank after hours and on weekends when the branch is closed. Not terribly helpful during business hours, right? In fact, it's actively harmful if you can't get that door open while the bank's running. And this is implicitly the model that we've got, I think, in a lot of encrypted databases, particularly when so much reliance is put on storage encryption at rest. So, can we encrypt data at the application level? Can we encrypt it before it ever leaves the boundary of the system? This should ring kind of familiar to the folks in this room because those workloads, certain ones have these kinds of end-to-end or client-side encryption requirements. So, simple healthcare record, we've got social security number, we've got contact information, presumably very sensitive information. If we can encrypt it at the application level before it ever touches the database, so that as far as the database is concerned, it's just a bunch of arbitrary binary fields. That would be really useful, and that's a powerful confidentiality protection. So it is similar to end-to-end encryption in messaging apps, the difference being the two ends are two different applications, or it could be an analyst and an application server and some other kind of integration point. But we don't trust the transit, we don't trust the storage centrally. Now, this isn't some sort of silver bullet, right? Because if you do have a running system where DBA level privileges are breached or access tokens are obtained, you can still delete records, you can still destroy them, but from confidentiality, it is similar in that sense. So we have end-to-end encryption, we have messaging systems, right? So can't we just take some of those technologies and apply it? It's a solved problem, right? It's not. Let's say you're a Python developer, a Java developer, a C# developer, you're doing Swift development on mobile, excuse me. If I say, here's an SDK, go figure it out, change the way that your queries work, change the way that you do inserts, updates, and so forth, it's not really an answer. And by the way, then if you do that, you have to re-engineer any kind of existing code, right? Because you can't just say, insert in a database social security number blah, search social security number X, and bring it. You can't do that. You've got to do all these kind of operations first. Well, but if you go through all that and you have really strong zero leakage, constructions, you can at least search your database, right, with all these software development kits. Nope. You can search by a reference or an indirect value, so like a customer ID or an account code or something like that, and bring an entire record back and then do decryption. But you can't actually search for, say, a credit card number or a social security number. And again, this doesn't count. Because the reality is, this is where developers live, right? How do you do AES padding again? Or I'm going to do AES because that's good, that's strong, that's modern, right? But what does all this stuff mean? CBC, CTR, OCB, which one again? Or I actually have got some working code that runs in Python. I do an HMAC, and then I do it in Java, and I get two different results. This is the world that most developers live in. They're not security experts, and they're certainly not cryptography experts. So about 2 years ago, this was the idea. There are lots of building blocks. There are lots of pieces of this that are just sort of waiting to be made easier to use by developers. Because we do, as a security and privacy community, I think we do focus a lot on how important usability is from end users. I don't think we talk so much about it for developers. I mean, I would argue it's just as critical, right? So what if we didn't have to use an SDK? What if we didn't have to rewrite all of our existing query code? And what if we could actually search a database, crazy idea, as a database is meant to do? What if you could just create a key, set a config, and go? So with that, we're off to the races. By the way, I think this should be like mandatory on every Enigma talk. They should just put this in the slide deck, right? So we built we refer to as client-side field-level encryption. The idea is that it's application-side encryption, but even further, it allows very detailed, granular encryption. So either down to the field or to an individual document, sort of the equivalent of a cell in a relational world. To give a sense of impact, and I only mention this because I think Mongo is sort of misunderstood, it is the widest, most used NoSQL database in the world. Everyone who has a smartphone in this room right now, you're running MongoDB. Your bank runs MongoDB. We have customers that are doing $60 billion a day in transactions on MongoDB. Major gaming platforms, healthcare, et cetera. It's got a huge impact. We run on 19 platforms, and I wasn't even really clear how to describe that, because that's not exactly true. We support 19 different languages. As an organization, we maintain 12 different driver language frameworks. There's about 7 or 8 that are kind of community maintained, but every major modern development language is supported. I think we've actually got Rust in the queue as well. And everywhere. So all the modern major operating systems, x86, ARM, mobile, Power, and yes, even IBM Z-series mainframes, we run at volume. So the implementation is We integrate this into the drivers in what we call the shell, which is sort of like a command line utility. All the encryption, decryption, again, because it's client side, is done in the driver on the client before the boundaries ever passed. In the MongoDB world, there's sort of the equivalent of SQL is called Mongo query language. It's a way of rich querying over JSON fields, both documents as well as nested subdocuments. And we built this in a way that automatic encryption can be done. So if you have an application and you say, insert social security number and then give it the value, I should be able to search for that and just do that. Like do an insert, do a retrieve, do a find, just like you normally have. This is one of the biggest takeaways I want to leave you with. We assumed when we were going into this that 95% of the work we were going to do was around cryptography. Probably 4%, 5% of the work was cryptography. 95% was taking a monster C++ code base and porting it to 19 different languages on all these different hardware platforms, on all these different operating systems. Because if you talk to a cryptographer and say, I want you to develop some kind of searchable database, some reasonable privacy leak margins, go. Well, in 2020, you might go a very different direction. Maybe you go on a modern flavor of Linux. Maybe you use sort of more recently developed constructions. But in the enterprise world, we have to support things going back 10, 12 years. We have to support ancient versions of Red Hat, ancient versions of Debian, ancient versions of Z-Series. And sometimes they don't even have things like SIV encryption. So then the discussion was, well, do we build that ourselves? Do we take some of these, the lower level primitives and kind of, put that together? And the very fast answer was twofold. A, no, don't do that. And two, look, we've got 600 engineers that work for us. We're pretty good at building distributed databases. We're not professional cryptographers. So very early on in the process, we decided, let's engage some of the best people in the field. If we want to do searchable encryption, let's bring in people who do that. If we want to do abuse-resistant AEAD constructions, let's work with people who do that. If we, at the end of this, when we're implementing this in all these different languages, we should probably have a pretty thorough security review by people who are both security engineers and cryptographers, like professional cryptographers. And so that's what we did. Again, just some of the details. Individual fields within a collection can be marked as encrypted or not, and keys can be used on a per field or per document basis. That last one's important because you could have in an application user keys, application level users, each have their own encryption key or multiple encryption keys. And so you could have a scenario where you say, just destroy this one user's key and all documents are irretrievable, even in backups. So that's really powerful, and it addresses some of the kind of GDPR sort of scenarios you can envision. So again, let's take a JSON record like this. In the Mongo world, the top three are flat records. The address field would be one of presumably multiple contact, so work, home, home to, et cetera. That's a nested document. We could say, let's just encrypt social security number or the street, or if you want, we can encrypt the entire subdocument. Because I know this is a cryptography enthusiast crowd, I'll share some of the mechanics. So we integrate cloud key services natively into the drivers. We didn't want developers to have to go through hundreds of pages of API docs to understand how Amazon works or Google's KMS system and so forth, or Azure's works. It's authenticated encryption, so an AEAD construction, an encrypted MAC. Again, it's abuse and misuse resistance. We have a couple different modes. So one is stochastic encryption with the narrowest leak profiles. We do offer we did engineer a deterministic mode for things like high entropy. If you were to create a histogram of a data field, something like social security number or credit card number is fairly flat and widely distributed. And so for those narrow cases, we can use something like deterministic search. Importantly, we called on the native OS libraries. So if you trust Windows for the CNG, if you trust Apple, if you trust Red Hat, if you trust NSS, or more importantly, if you've got an entire compliance framework that's built around attestations or validations or things, I could give an entire talk about the problem with FIPS, but if you are in that world, you can still take advantage of those. But also from a practical perspective, every time there's some small timing attack or side channel, you don't have to update your database software or your drivers, you just update the underlying operating system and you pick that up, it sort of comes with. So application side, client side is the model. Within that context, we try to use reasonable security hygiene. There's no security guarantees around the application side. So if your app server who actually takes in clear text, a raw healthcare record, a raw financial record, a raw contact information, if that's compromised, this won't help. But this isn't meant to be a silver bullet. It's meant to add some additional controls around a central model so that if an attacker were to have DBA level privileges, if those access tokens were breached, they'd have to do one more step, which is to get the encryption keys as well, which significantly raises the bar on attacks. So stored field keys are protected by strong symmetric encryption. If we only had one or two, we could store that client side. This is another area where the academic world, I think, diverges vastly from practice. A lot of structured searchable encryption assumes that you can build complex index trees and things on your application. But that assumes you've got one application server and one database. What if you've got thousands of nodes in a cluster globally and you've got thousands of application servers? Now you've got two problems because you've got to maintain state between all of those, both at the DB level, and presumably your database already handles that, but then also at the client side. So that didn't make sense. So what we can do is we can actually store those field encryption keys in the cluster itself. Well, why would you put encryption keys on the very database you just said you don't trust? We're protecting it with symmetric encryption, and the decryption keys are never stored there. So we can use all the replication, all those other benefits. If you basically trust AES to protect your data, you should trust AES to protect your keys. In the cloud context, so most of the providers have an HSM-backed, root trust within their KMS. Also, I don't have the exact timing, but within days to weeks, we'll be publishing the security audits that came from this. So I should mention specifically, so on the authenticated constructions, we worked with Kenny Patterson at Royal Holloway to help come up with really interesting attacks and protections early on. We worked with Seni Kamara's team at Brown University. His startup is called Aroki on searchable encryption, and then JP Amason, who you may be familiar with, did the security audit on, I think, 6 different language platforms. And so we'll be releasing those audits publicly very shortly. We didn't design it this way, but it turns out because we're using symmetric encryption everywhere, some of the core constructions turned out to be post-quantum kind of as a side benefit. I'm pretty skeptical on quantum computing in general, but if that's your thing, we provide some margins against that. So let's open the safe. Let's actually use a database for the way it's encrypted. This is the magic one, right? So this is a line. I want to find the social security number. Behind the scenes, client-side field level encryption looks at that, says this field's been tagged as encrypted. It's been marked with a certain encryption mode. We can't ask the database for social security number 901 because A, it's not going to find it, and B, it's not going to know what to do with that. We've actually got to ask it for the encrypted value for that to return back. So from the database's perspective, you could be asking for anything. It happens to be a string or an integer or what have you that you've already declared, but this is the translation that happens sort of behind the scenes. And then on the return side, what's handed back to the application is the raw clear text. A couple of sort of lessons from this. Dependencies are insane. I am not at all a Windows developer, but one of the side effects of doing some of this work, I should mention too, by the way, we had 24 engineers full-time dedicated on this for 2 years. This is a major, major amount of work on all these different platforms and languages. I had no idea. I sort of had a little idea, but I didn't really have a big idea how fragile some of the package managers and dependencies were. There are flavors of Python where it's like burning sagebrush and doing incantations and like praying to the gods the right way. And so these kind of practical matters, it may seem trivial, they may seem like kind of just, details, but if it's the difference between a developer never getting up and running because they can't get these installed, that's critical. Same with Go. Go has a way to wrap C libraries. What I discovered is Go doesn't have a distro. There's no real clear native way to do binary distributions for Go libraries. So that was kind of challenging. I also learned every way to torture Maven possible. So it was kind of a fun personal experience as well. They don't teach you this in Computer Science 101 or 102 or 501. No one reads the docs, and I mean no one. We did probably 20 usability studies where we brought developers in blind, gave them access to all and they were varying levels of proficiency. Some were 10-plus year veterans, some were a couple years out of school. I learned so much about different sort of ways that at one point we had people that were literally trying to compile on Mac, like Python, like actually compile the underlying C libraries on Python. Like, no, you don't have to do that. Just add this extra flag and just do an update and you'll get it. So operating systems have some of the weirdest libraries you can imagine. There's literally something in OpenSSL I discovered called Hobble, which is, I think, it traces its lineage back to the export level, export era encryption days. Just to get to Hello World took months of documentation, of tutorials, and we still got a ton of work to do. But I guess part of one of the lessons is make those copy-paste examples easy to use, contained, because the web's going to do it for you, and the web's going to do it really, really badly. Encrypted search has costs. One thing I want to disabuse folks of, and I'm happy to kind of get into the weeds for folks who are in this area. If you were to read popular media reports, one could come away with the impression that homomorphic encryption is sort of going to save us all because it's got all these wonderful properties and we've had all kinds of improvements around performance. And it's true, we have made sizable performance impacts. But I think homomorphic encryption is misunderstood. It's meant for calculating integers. I don't know about you, but I store strings in my database. I do searches. It's important to do things like adding numbers, but that's it's kind of a narrow element. And doing things like wildcard searches, begins with, ends with, there may be some other options. And in fact, one of the things that surprisingly few people are talking about is structured searchable, searchable symmetric encryption. It has some really promising properties and artifacts, but just isn't seeing much publicity. And I'd like that to get a little bit more visibility. Every database developer has some native functions that they like. In the Mongo world, there's something called the aggregation pipeline, which lets you do these multi-stage pipeline analytics. If you offer some kind of encryption solution, but then give back 1% of what a developer's used to, you're not really offering much. You're not really offering a practical solution. Key management. You can't underestimate how complicated this can be. I don't know very many people who actually really understand IAM, identity access management. I'm not really clear any one person really does outside of the major cloud providers. And again, one of the things from this is that probably 5% or less of the actual engineering that we did was cryptography. The rest was all around the developer ecosystem. We don't control, for example, the Node repositories or the Java repositories or Go. We can contribute to them. We can sort of nudge in certain directions. But there's a huge ecosystem of practical concerns and considerations that have to be taken into account, particularly on a platform with this wide reach of users. Engage professional cryptographers early in the design if you're going to enter this world at all, right? Again, I could do a whole talk on homomorphic encryption and how it broke my heart years ago. Developer ease of use is more important than technical properties. We can give people choices, but if they don't have the information to make sense of those choices, they're not real choices. And we have to make those choices easier. And with that, I'll stop. Thank you.